This is Dr. Holt. This lecture, AP Physics C, is on the conservation of momentum and collisions. I'm going to work some miscellaneous type problems. The first problem we have is a cannon is rigidly attached to a carriage which can move along horizontal rails but is connected to a post by a large spring initially unstretched with a force constant of K of 2 times 10 to the 4th Newton per meter as shown below. The cannon is going to fire a 200 kilogram projectile at a velocity of 125 meters a second, directed 45 degrees above the horizontal. If the mass in the cannon is 5,000 kilograms, we want to do several things. We want to find the recoil speed of the cannon, and we want to find the maximum extension of the spring, and then find the maximum force the spring exerts on the carriage, and then we want to look at is the momentum of the system conserved during the firing. So let's look at part A first. Okay, we want to find the recoil speed of the cannon first. Now if you look at this picture, we can tell that the system itself is going to move to the left. So we know that the initial momentum before it is fired in the x direction is going to equal 0, and we know the momentum in the initial y direction will equal to 0. So we will look at just the x to start out with. So we're going to set the final momentum in the x direction must also equal 0 because we have the conservation momentum. So we can say that 0 is equal to the mass of the shell, 200, times its velocity, which was 125, times the cosine of 45 degrees, plus the mass of the cannon and its system, which was 5,000 kilograms, times v of x must equal to 0. When we solve for that, we will get vx, and we'll put the c for the cannon. It's going to equal to negative 3.54 meters a second. So we know this whole system is going to move to the left at a velocity initially, right when it's fired, of negative 3.54 meters per second. And that would be the answer to A. B says find the maximum extension of the spring. So let's go look at that real quick. To find the maximum extension of the spring, you want to go back to an energy equation that we know the kinetic energy initial of the system plus the potential energy of gravity initial plus the potential energy of the spring initial must equal to the kinetic energy final plus the potential energy of gravity final plus the potential energy of the spring final. Okay, now this is right after you've fired. So we know this system here is going to move to the left. It's going to go this direction here. So we'll figure out what the kinetic energy of that part would be. That would be 1/2 times the mass, which is 5,000, times this velocity, which we said was minus 3.54. We'll square that. We're just doing 1/2 mv squared. The gravitational potential would be 0, and the spring potential would be 0, right at when you fire. Now, when it comes to a stop, the kinetic energy here has gone to 0. Obviously, there will be no gravitational potential energy, and we'll just set this equal to the spring potential, which would be 1/2 times k, and we know our value of k, which was given the problem, is 2 times 10 to the 4th times x squared. Alright, when you run that, you'll find that your displacement is going to be in this case plus or minus because you have the square root, would be 1.77. So the spring has extended 1.77 meters. And again, the negative's only in there because I have everything going to the left. And that's why I'm showing this as negative. Okay, part C, find the maximum force. Well, we can do that very quickly. Let me write this as B. We can do that very quickly because we know force on a spring. The maximum force would be when it's fully stretched, and that's going to be going back to the right, and that is always equal to K times X. So we put the values in as 2 times 10 to the 4th, and then we're going to put in how much is it's going to be stretched, 1.77. We'll run that number, and that's going to give me 35,400 newtons. And again, that force in the spring's going to be trying to pull it back this direction here. Okay, let's look at the last question. Is the momentum of the system conserved during firing? The answer to that is going to be no. The rail itself is going to exert a vertically external force on the cannon, and it will prevent it from recoiling vertically. Momentum is not conserved in the vertical direction. However, in the horizontal direction, momentum will be conserved. Let's look at this problem here. We have two carts, equal mass, 0.25 kilograms. They're going to be placed on a frictionless track that has a light spring, a force constant 50 newtons per meter right here. It's attached at one end as shown below. The red cart is given an initial velocity of 3 meters a second. To the right, the blue cart is initially at rest. Find the cart's velocity just after the first collision. One thing to note on this one, if the velocity of the red initial is 3 meters a second, and it hits a cart that has a velocity that is 0, we'll call the blue initial is equal to 0, then after the collision, if the two masses are the same, velocity red final will equal 0. It will transfer all its velocity to the second mass, and then the velocity of the blue final will equal to the 3. Alright, so that's going to be the question. The answer to part A would be the velocity of the red would be 0, the velocity of blue would be 3. Now it says find the cart's velocity just after, it says find the maximum compression of the spring. Alright, this becomes an energy type problem. Scroll down just a little bit here. We can say that the potential energy initial of gravitation plus the potential energy of the spring initial plus the kinetic energy initial must equal to the potential energy final of gravity plus the potential energy of the spring final plus the kinetic energy final. That has to be constant, and I'll just fill these in. Obviously we have no gravitational potential, so put 0 here. If the blue card is going to the right red, we have no potential energy. So all now we're going to have is kinetic energy. Again, that goes 1/2, and the mass is 0.25. And the velocity is going to be 3, so we're going to square that. We're going to set that equal to this. Potential energy, gravitation will be 0. Now the kinetic energy here, once it stops, will be 0. So we're just going to set this equal to 1/2 times the spring constant, which is 50, times x squared. Because remember, the potential energy of a spring is 1/2 kx squared. And now all we have to do is solve for x, and when we do, in this case, we'll get a value of 0.212 meters. Okay, relatively simple problem. Okay, in this problem here you have a 25-gram object moving to the right at 20 centimeters per second. It overtakes and collides elastically with a 10-gram object moving in the same direction at 15 centimeters per second. Find the velocity of each after the collision. Alright, so let's go ahead and label this. We'll label this in terms of meters per second. The reason I'm doing this is because when you have elastic, you have to consider kinetic energy also. We'll label this as 0.15 meters per second. and we'll label this as 25 grams. And you can convert the 25 grams back to kilograms if you want to. It's not going to make any difference in this problem here. Alright, on this problem you want to find out what the initial momentum is going to be, because you know with elastic collision, and actually with any type of collisions, that initial momentum will equal to final momentum unless additional forces are being added to the system. And we also know that kinetic energy initial is equal to kinetic energy final. Again, that is, the kinetic energy is only for elastic collisions. So let's find out what the initial momentum will be. That'll be mass times velocity. That's a vector quantity, so we're going to let anything goes to the right be positive. That's 25 grams times 0.20 plus 10 times 0.15. Okay, that's our initial momentum. We will set that equal to 25. We do not know what the velocity final is going to be for the other one, or for the 25 gram object. And we'll do the 10 the same way. We'll make that V10. That's our equation. We will simplify that. That's going to give me, I'll do it over here, I'll just draw a line here. 6.5 is going to equal to 25 V25 plus 10 V10. Alright, so that's really our first equation we want to use. Now we immediately go back to kinetic energy. I'm going to scroll down just a little bit. Our kinetic energy is going to be, like we said, initial equal to final. So we'll go back to 1/2 times our mass, 25, times 0.20 squared, plus 1/2 times 10 times 0.15 squared is equal to 1/2 times 25 times V25 squared plus 1/2 times 10 times V10 squared. Alright, we'll make life a little easier. We'll cancel out the 1/2 on all sides. We'll rewrite this equation, and we are going to sum up all the left side as we do. When we do that, we'll get one. Oops, I don't want purple. We will get 1.225 is equal to 25 V25 squared plus 10 V10 squared. Okay, that's our second equation. Alright, so we have two equations. We have this equation and we have this equation here. We're going to take this value right here and we're going to solve for V25. So we'll move everything to one side and we'll divide by 25. When we do that, we will get V25 is equal to 0.26 minus 0.4 V10. So what we're going to do now is we're going to take this value right here and we're going to substitute it back in for this one right here, and we'll rewrite that equation. So when we do that, we're going to get 1.225 is equal to 25. Put this in parentheses. I'll rewrite this, just switch it, just make it a little easier. 0.4 V10 plus 0.26 plus 10 V10 squared. Oh, I need to put the square up here, sorry. Okay. What we're going to have to do here is you need to FOIL this. So we'll go ahead and do that. 1.225 is equal to 25. When we square this, that's going to give me 0.16 V10. And you got to make sure you square that. Then we're going to multiply 0.4 times 0.6 and then multiply by 2 because we're foiling it. And that's going to give me minus 0.208 V10 and then 0.26 times 0.6 is 0.0676. Alright, and then plus 10 V10 squared. We'll go ahead and solve that. We'll get 1.225 is equal to 4 V10 squared minus 5.2 V10 plus 1.69 plus 10 V10 squared. Okay, we have a quadratic equation here, so what we want to do is we want to set it equal to 0. We want to move everything over to the other side. We're going to add the 10 and the 4 together. That's going to give me 0 is equal to 14 V10 squared minus 5.2 V10 plus 0.465. Okay, you can solve this now, either graphing it, quadratic equation, or if you got a program written, you can solve these type of problems. When I do that, you're going to get two answers, and that's what you got to be really careful with. You're going to get V10 is equal to 0.15, and you're going to get V10 is equal to 0.2214. You want to take these two values here, put it back into this equation here to find out what V25 is. When you put the 0.15 in, you'll get V25 is equal to 0.20. You put this value in here, V25 is equal to 0.171. And again, these are all these are meters per second. Let me just do that. Okay, now let's go back and look at our picture here. The 25 is on the left side. So if the 25 is on the left side, this cannot happen. The 25 would have to go through the V10 to be going faster than V10. So this one is incorrect. The correct answer to this problem here is going to be this right here. 25 is going to be slower than V10, because that's the only thing that could really happen, because the 25 cannot go through the V10, and this would be the correct answer.